Section 8-2 is on critical points and points of inflection. The objective of this section is to use the first and second derivative of a function to find critical points and points of inflection. If you recall from the first part of this section, we talked about how you can use the first derivative of a function to help you find where the function is increasing and decreasing. You can also use it to help you find where the minimum and maximum and plateau points are. And we also looked at the fact that the second derivative tells you where your function is concave up and concave down. And if you change concavity, you have a point of inflection. So we can use first derivative and second derivative to help us find those different features of our graph. We're just going to continue with that using those number line graphs that you were introduced to. But we're going to look at it from somewhat of an algebraic standpoint here as well in this next part of this section. All right, so let's start out with an example here. The example 3 there in your book says the figure there shows the graph of the derivative of a continuous piecewise function f defined on the closed interval from 0 to 8. It says on a copy of the figure there, sketch the graph of f given the initial condition that f of 1 is equal to 5. Put a dot at the approximate location of each critical point and each point of inflection. Okay. So here's our sketch of this, actually not the function, but the derivative of the function. We're looking at f prime here. And the question is, what does function f look like? Now, you've done this before where you're given a sketch of either f and asked to sketch what f prime looks like, or given a sketch of f prime, asked to sketch what function f looks like. But we're going to get a really accurate sketch after we go through this process of using not only the number line graph, but also the relationship that I know f prime has with function f. We'll use both of those to help me come up with a pretty accurate sketch of function f. So let's start with this. Let's start with the number line graph here. And it's usually easiest if we sketch the number line graph right below our function. And so we're going to have f prime of x and f of x. And we're going to mark just our critical points as we do this. So at 0, we have an endpoint here. So that's going to be a critical point for us. Remember, the critical points are where f prime of x is equal to 0 or undefined. So those are the points that we're going to mark here. In fact, I'm going to go ahead and mark that down here. It's f prime of x equals 0 or undefined are the points that we are going to mark along this axis. So I can see that we are equal to 0 right at 1. So 1 is a critical point for us, and f prime is 0 there. It looks like at 3, f prime is at 0 again. It crosses the x-axis there. At 4, this thing's undefined. I'm going to go ahead and just write that it's infinity there. If you wanted to say that it's undefined, you can do that. Just for ease of writing it, I'm going to say infinity, though. And then at 6, I can see that we hit 0 again. And then finally at 8, we have an endpoint at 8. So a lot of those points get marked. But notice that we're not marking all the points from 0 through 8, just the critical points of function f. And now what I want to do is fill in between these what function f prime is doing, whether it's positive or negative, and that will tell me something about function f. So if I look between 0 and 1, start on the far left here, between 0 and 1, my derivative function, I'm looking at the derivative there, is above the x-axis. So that means my derivative is positive, so I'm going to put a little plus sign there. And then between 1 and 3, my derivative is below the x-axis, so that means my derivative is negative. From 3 to 4, we're above the x-axis again, so we're positive. From 4 to 6, we are below the x-axis, so it's negative. And then from 6 to 8, our derivative is above the x-axis, so therefore f prime is positive. And now I can fill in what that means about function f up above this. So up in that top row here of my number line graph where I have f of x written over on the left side, I start out at an endpoint, and then after that from 0 to 1 I'm increasing. So we draw an arrow indicate I'm going up. And then I hit a horizontal slope, so I'll just draw a horizontal arrow there. And then from 1 to 3 we're decreasing, so we'll draw in our decreasing arrow. And then at 3 we have a slope of 0 again, so I'll draw a horizontal arrow. And then from 3 to 4 we're increasing again. We hit a vertical slope there at 4, so we draw a vertical arrow. And then from 4 to 6 we're decreasing again. At 6 we hit a horizontal slope. And then from 6 to 8 we're increasing again. All right. And let's fill in what that means about our function as far as our minimums and maximums and plateau points if we have them. But it looks like that we start out at an endpoint and then increase after that on the left side here at x equals 0. So this must be a minimum right here. So we'll say min. And then at 1, we are increasing just before that, decreasing after it. So this must be a maximum. And then at 3, we're decreasing, then increase after that. So that must be a minimum. At 4, we actually hit a vertical slope, but we were increasing prior to that and decreasing after it, so it's actually a maximum. But the fact that you hit a vertical slope like that means that we're going to have a cusp in this thing. In fact, I'll go ahead and add that on there. From 4 to 6, we're decreasing, and then at 6, we hit 0, a slope of 0, and increase after that, so that must be a minimum at that point. And we increase all the way to that end point at 8, so that means that this must be a maximum at that end point. All right, so there's the information that we get from the first derivative. Now let's take a look at the second derivative. And again, I'm going to try to sketch this right underneath the number line graph I already have there. Probably should have scooted that over a little bit so that I had some room over here on the left, but I got f double prime. I'll try to squeeze that in there, and then f of x. And again, any of the critical points or any points where we are undefined in the first derivative, we're going to have the same in the second derivative here. But at 0, we have an endpoint we can mark. And the points that we're marking now, these are the critical points of function f prime. So that's where f double prime is equal to 0 or undefined. That's what we're going to mark along here. So I got to think about the derivative, where the derivative of the function that I'm looking at is equal to 0 or undefined. So again, I got to consider the slope of this thing. If you look at the slope of this, when I hit a value of 2 at x equals 2, I have a horizontal slope there. So at x equals 2 is a critical point. So I'm going to mark that here. And the slope of f double prime would be 0 there. Continuing on, at 4, my first derivative was undefined there, so my second derivative is also going to be undefined, but you can see that you have a step discontinuity there. And then from 4 to 6, again, considering slope of this thing, slope is constant, but it's not a slope of 0 there. So all the way to 8, where we have an endpoint, is the next critical point. Again, the key there is you're looking at the derivative of f prime here. That's f double prime we're working with. So now think again of what the derivative would be of this function, whether the derivative would be positive or negative. So from starting on the left here, from 0 to 2, my function starts out here, f prime is decreasing. So that means its slopes are negative. So f double prime would be negative. And then from 2 to 4, the function there is increasing. F prime is increasing, so its slopes are positive. So that means f double prime would be positive. And then finally from 4 to 8, our function is increasing that whole time there. So f prime is increasing means that f double prime must be positive. All right, so now let's fill in what that means about function f of x and its concavity, remember. So from 0 to 2, this function has a second derivative that's negative, so that means that f must be concave down. From 2 to 4, the second derivative is positive, so our function must be concave up. And from 4 to 8, it's got a second derivative that's positive, so we're concave up still. And again, if we fill in what that means in between these values here, or in between these intervals here at these critical points we marked, at x equals 2, we can see that we go from concave down to concave up, so we have a point of inflection. We'll say POI right there for point of inflection. At 4, though, we were concave up prior to that, concave up after that, so there is no point of inflection. We did not change concavity. Remember, you have to actually change concavity for you to have a point of inflection there. Now, from this, I could actually get a pretty accurate sketch of what this graph looks like. I know whether it's increasing or decreasing. I know the shape of it as well. But we can actually go a little bit further because they gave us a point here to start out with, unlike the first two examples that we saw. Here they gave us a point, and the point that they gave you here was that f of 1 is equal to 5. So I'm going to go ahead and mark that point here, that f of 1 is equal to 5. That's this point right here. F of 1 is equal to 5. And I can use the fact that I know a relationship between f prime and function f using the fundamental theorem of calculus to help me come up with some points, or some pretty accurately, some points that this must go through. Here's the property. If you recall, your fundamental theorem of calculus says that the integral from a to b of f prime of x dx is equal to the antiderivative of f prime, that would be f, evaluated at the upper bound, minus the antiderivative, that would be f, evaluated at the lower bound. That's our fundamental theorem of calculus. And so in our case, we know what f of 1 is equal to, and I could use that to help me find another value of f. And so that's what we're going to do here. So in particular, let me just solve this for, I guess in this case we'll solve it for f of b. If we were to solve for f of b, we'd have f of b is equal to, I'll move f of a to the other side, so it's f of a plus the integral from a to b of f prime of x dx. If you recall, we've worked with some problems just like this. We've used 1 point to help us come up with additional points that our function must go through given a derivative of our function. And so that's what we're going to do here. I'm going to find out what f of 2 is equal to. F of 2 is equal to, I'm going to use 1 for a, since I know what f of 1 is equal to. They told me that. Plus the integral from, it's a to b, so that's going to be 1 to 5 of f prime of x dx. So, f of 1 they told me was 5. And the integral from, oops, not 1 to 5, I'm sorry, it's 1 to 2 is what that should be for the upper bound. The integral from 1 to 2 of f prime is just the definite integral here, or the area under the curve from 1 to 2 on our function. So I can approximate that by counting squares. It's this little section, I'll just kind of draw it here. It's this little section right here. Now it's below the x-axis, so it's going to be negative. And that looks like it's probably got an area of about 0.6. So let's say that's a negative 0.6. Now again, you're approximating here, so if you thought it was negative 0.7 or even negative 0.5, that's probably close enough for us. But let's say that's a negative 0.6. So that's going to be 4.4. So I know now that f of 2 is equal to 4.4. So I can come over here to 2 and plot a point of 4.4. And I can continue doing this. I'm going to do this for several more points. Actually, I want to do this for the rest of the points here that we have. So f of 3, got those kind of in my way here, is going to be equal to f of 1 plus the integral from 1 to 3 of f prime of x dx. I don't know if I can move this here. I'm just going to move this out of my way. Actually, I'm just going to delete this for right now because I've already marked it. Just get both those out of the way so I can draw this in here. All right, so f of 3 is equal to 5 plus the integral from 1 to 3. Now, from 1 to 3, that would mean that we've already calculated what it is from 1 to 2, so it looks like this is going to be an additional negative 0.6 right here. So a negative 0.6 and negative 0.6 is a negative 1.2. So plus a negative 1.2 is going to end up giving us 3.8. So up here on our graph, we're going to plot a point at 3, a value of y equals 3.8, which we'll say is about right here. And now we can move on to the next point. We'll find f of 4. Now you can keep writing down the equation if you want to, but I think we get the idea here. It's going to be 5 plus the integral from 1 to 4 is what I need to calculate. So from 1 to 4, now we're above the x-axis, so I've got to count up these 3 squares here. This looks like this is about 0.8. This one looks like it's about 0.4. And this one here looks like it's about 0.1, we'll say. So 0.8 plus 0.4 is 1.2 plus the 0.1 is 1.3. So we have a negative 1.2 from 1 to 3, and then a positive 1.3 from 3 to 4. So that gives us a value of 0.1 is what those should add up to be, it looks like. So this turns out to be equal to 5.1. So we're increasing back up to this value here of 5.1, it looks like. So at 4, we get a value of 5.1. So it'll be up there. All right, let's find out what f of 5 is equal to. It's going to be 5 plus the integral from 1 to 5. So we've already calculated the integral from 1 to 4. We just got to add on the piece from 4 to 5. So this looks like a full square here, and this looks like half a square here. But these are below the x-axis, so they're negative. So it's a negative 1.5. So if we add on the negative 1.5 to the 0.1 that we had from previous, we end up with a negative 1.4. So we end up with 3.6. And we get 3.6 is right about here. And now for f of 6, that's equal to 5 plus our definite integral. Looks like this is a negative 0.5. So we got to add on another negative 0.5. So the negative 1.4 plus a negative 0.5 is a negative 1.9. So that looks like that's going to be 3.1. And so at 6 we get 3.1. So we're about right here. And for f of 7, we end up with 5 plus the area from 6 to 7. We have to add on to this thing. 6 to 7, now we're above the x-axis, so that's a positive 0.5. We'll add on the positive 0.5 to the negative 1.9 that we had before to get negative 1.4. So we get 3.6. And we'll plot a point at 3.6. And finally at 8, f of 8 is equal to 5 plus the integral from 1 to 8, which we've already calculated the integral from 1 to 7. We just got to add on the integral from 7 to 8. So this looks like this is a positive 1 and a positive 1.5. So we add on 1.5 onto the negative 1.4 that we had. We get a positive 0.1 to get 5.1 is where we end up with. So we will plot that point at 5.1. And actually we can go back and find out what f of 0 is equal to. To find out f of 0, I'm going to write this one out here though, just so we realize it's a little bit different. F of 0 is equal to f of 1 plus the integral from 1 to 0 of f prime of x dx. And notice that my endpoints there are switched around. I have the lower value on the top. So remember, that's the same as the opposite of the value from 0 to 1. So it's the opposite of the integral from 0 to 1 of f prime of x dx. So I need to take f of 1, which is 5, and subtract this value. So let's find out what the integral from 0 to 1 is equal to. And actually, it looks like there's some symmetry here. So we've already calculated these here. This is 0.8, this is 0.4, and this we said was 0.1. So that's going to be 1.3. So we end up with 5 minus 1.3, which gives us a value of 3.7. And so we'll plot that. At 0, we're at 3.7, so that's about right here, we'll say. Okay, so notice that we've come up with some points that our curve actually goes through, or some pretty accurate points that it looks like the curve goes through. And not only can I use that to help me get a pretty accurate sketch, but now I can use my number lines to help me come up with an even more accurate sketch. So look at what's happening here from 0 to 1 on my function. From 0 to 1, my function starts out at an endpoint, and it's increasing from my first derivative, and it's concave down. Well, that tells me the shape of this thing that's increasing and concave down. It has to have this shape here. Continuing on from 1 to 2, my function now is hit a slope of 0 at 1, and then from 1 to 2 it's decreasing, and from 1 to 2 it's still concave down. So it's going to decrease and hit this point right here at 2. And then from 2 to 3, my function is still decreasing. It's going to hit a slope of 0 at 3. And it changes concavity now. It now becomes concave up. So now this thing has a graph that looks something like that. It should have a slope of 0 there. I didn't quite get a slope of 0, but we're close. From 3 to 4, this thing is increasing now. It's going to increase towards this maximum where this cusp is at. And from 3 to 4, we're still concave up. So it's going to look something like this. From 4 to 5, the function is now decreasing from my first derivative. I can see that. And it's now concave up. In fact, it's concave up for the rest of this thing. So it's decreasing and concave up. So it's going to look something like this. And in fact, from 4 to 6, it's decreasing this whole way. But since I had 5 plotted here, that's why I stopped there. But from 5 to 6, we're still decreasing towards a slope of 0 and concave up, like I said. And then after 6, it's now increasing from 6 to 8, and it's still concave up. So from 6 to 7, we're increasing and concave up. 7 to 8, we're increasing and concave up. And that right there is a pretty accurate sketch of what function f of x must look like. Not only am I pretty close on the points that it actually goes through, so I know how far it actually increases or decreases, but I also know the exact shape there, whether it's concave up or concave down as well. All right, let's take a look at another example. We're going to jump to an algebraic solution for this one here. The last, actually the ones you've been working with here have been graphical solutions. Let's look at an algebraic one. Figure 8.2k says, shows the graph of f of x equals this function. So let's write down that function. F of x is equal to x to the 4/3 plus 4 times x to the 1/3. Now for part A, it says sketch the number line graphs for f and f, or for f prime and f double prime that show the features that appear clearly on the graph. Now I'm going to skip past that because that's what we've done in the previous several examples. So you can look back to those to get some more practice with that. But let's look at part B. Part B says find equations for f prime of x and f double prime of x and show algebraically that the critical points you drew in part A are correct and fix any errors. All right. In fact, we're going to find out here, just looking at the sketch there, it's not as easy to determine all of the critical points there. And this is where an algebraic solution is a much better approach. So to find the critical points of f, in fact, I'm going to label it this way, critical points of f. To find the critical points of a function, you find where the derivative of that function is 0 or undefined. So I've got to find f prime of x. So f prime of x is equal to 4/3 x to the 1/3, use your power rule here, plus 4 times 1/3 is 4/3 x to the negative 2/3. And again, the critical points of f are where f prime is equal to 0 or undefined. Don't forget the undefined part. That's the part that's forgotten. All right, to find out where this thing's 0 or undefined, I'm going to do a little factoring with this. These both have a 4/3 as a factor. In fact, they both have powers of x. I'm going to factor out the smaller of those two, just like you do whenever you're factoring out x's. So the smaller of the two is the negative 2/3. And so if I factor or divide that out, I'll be left with just an x in the first term there. You can multiply those together and you'd see you get 4/3 x to the 1/3 there. Add your exponents, the 1 on the x and the negative 2/3 there gives you a positive 1/3. And then we factored everything out from the second term, so we're just left with a 1. We need to find out where this is 0 or undefined. All right. One last step here, although you don't necessarily have to do this, but it might help in recognizing where this thing's undefined. If you have x to the negative 2/3, that's actually 1 over x to the positive 2/3. I'm going to write it that way just so it helps us see our two critical points that we should have here. All right, so we get it factored this way as 4/3 times 1 over x to the 2/3 times x plus 1. All right, so as far as where this thing's equal to 0, well, it's equal to 0 when the x plus 1 gives me 0. So x plus 1 would be equal to 0 at a negative 1 if I plug in a negative 1 there. Of course, there's nothing I'm going to plug into the 1 over x to the 2/3 to make that 0. You can't divide by anything to get a 0. However, if I let x be 0 in that, I'd be dividing by 0, so I'd be undefined. This is why you have to make sure you check to see not only where f prime is 0, but also where it's undefined. So we get two critical points, one at -1 and the other one is at 0. All right, let's find the critical points of f prime now. Again, to find the critical points of a function, in this case f prime, you find the derivative of that function and you set it equal to 0 or find where it's undefined. So we find the derivative of f prime, that's known as f double prime. So I got to find the derivative of f prime. So you could actually work with any one of those equations that we have here for f prime. I'm going to work with the very first one just so that I don't have to use product rule or quotient rule. But you could technically use any of those. So if I take the derivative of that very top line there, I'm going to get 4/3 times 1/3 is 4/9 x to the -2/3. Plus, I'm going to get, actually it's going to be minus here, so I'll go ahead and do that. I'll change that subtraction. It's going to be a minus -2/3 times 4/3 is a -8/9 x to the -5/3. And that's equal to 0 or undefined. We need to find out where the derivative of f prime, that is f double prime, is equal to 0 or undefined. And now let's do some factoring like we did before. We'll factor out a 4/9 and we'll factor out x to the -5/3. So we'll be left with an x in the first term and then a -2 actually in the second term there. Go ahead and multiply that through just to see that you get in fact the original equation there. And we want to find where that's 0 or undefined. And now again, it's up to you whether you need to make this next step. I'm going to go ahead and write this down though. X to the -5/3 is 1 over x to the 5/3. Again, the first couple times you see that, you might want to write it down just so you remember that you're going to have division by 0 there when x is 0. So my two critical points are where x is equal to get the 0. If the x minus 2 would give me a 0 when x is 2. And to get this thing undefined, again, if I plug in 0, I'm going to be dividing by 0. So I find two critical points for f prime. All right, so we found the equations, and you can check to see if you've got the correct points that you had from the graph, although I think some of these are not quite as easy to see just looking at the graph. In fact, I think the one at 0 there is not quite as obvious that that thing has a second derivative that would be 0 just from the graph. But let's draw the number line graphs from these. And so we end up with, oops, I don't need a line that big. We end up with the following, and I'm going to try to sketch these two right on top of each other. I don't need to resketch the original function because you already have that, but I'll sketch the number line graphs, if you will, kind of visualize the original graph right above this. So we've got f prime of x, and f of x, and f double prime of x, and f of x. And so my critical points for f prime were at -1 and 0. And my critical points for f double prime were at 0 and at 2. Okay. And for f prime, this was equal to 0 at -1, and it was equal, the second derivative was equal to 0 at 2. And in both cases, we are undefined at the 0. So again, I'll use infinity there. If you want to put UND or something like that for undefined, that's fine as well. But as long as we understand it's undefined there, it doesn't matter for us whether we write it this way or write it as undefined. All right, now what we need to do is figure out what's happening in between these values on f prime and f double prime. So let's start with f prime. So for f prime, I'm going to take and pick a point that's less than -1 to the left of that 0 that we had there, and see whether we get a positive or negative value. Now all I'm worried about is the sign, so I don't care whether it's what the actual number is. I just want to know whether it's positive or negative. So I'm going to look at this last way that we wrote it in this factored form and figure out whether it's positive or negative. So when I plug in a -1, for example, let's plug in something to the left of -1, so like -2. When I plug in -2, the 1 over x to the 2/3 power, the 2 in the numerator tells me I'm going to square that. So if it's negative, When I square it, the 1 over x to the 2/3 becomes positive. So I've got 4/3, which is positive. 1 over x to the 2/3, that's positive. And then I have a negative 2 plus 1, that would be a negative number. You'd end up with a positive times a negative. We end up with a negative result. Again, notice I don't care what value it actually is. I just want to keep track of the sign. Now pick a number between -1 and 0 now. So between -1 and 0, if again, the 4/3 is positive. The same argument would tell me that 1 over x to the 2/3 is going to be positive. So it really comes down to this last factor here, x plus 1. If I plug in a -1/2 and add 1 to it, that becomes positive. So I have a positive times a positive times a positive. This is positive. And now look what happens after 0. Let's plug a value like 1 in. 4/3 is positive. 1 over x to the 2/3 is always positive. 1 plus 1, that's positive. So we end up with a positive times a positive times a positive. So here's what our first derivative number line graph looks like. And so this function is decreasing, and then it levels off to a slope of 0 there at -1. And then it's increasing. It has an infinite slope there right at the origin, and then it continues increasing after that. So in this case, this function has a minimum right here at -1. All right, let's do the same thing for the second derivative. Come back up here to our second derivative test, and or our second derivative equation here. And I'm going to look at this last way that we wrote this. Again, you could work with any one of these, but this is the easiest one to work with in terms of finding the sign. So we're going to plug in a value that's less than 0, like -1. And if I plug that in, the 4/9, of course, is positive. 1 divided by x to the 5/3. Now, taking the cubed root is going to keep the sign. Raising it to the 5th power is going to keep the sign. So that's going to turn out to be negative when I plug in a negative number. And -1 minus 2, that's going to be negative. So I've got a positive times a negative times a negative. That turns out to be a positive result. Plug in a number between 0 and 2. So like 1. If I plug in 1, 4/9 is positive. The 1 over x to the 5/3, that would be positive. And then 1 minus 2, that's a negative number. So positive times a negative gives me a negative result. And the last one there, if I pick a number greater than 2 to plug it in, if I pick, for example, 3, 4/9 again is positive. 1 over x to the 5/3, again, that's going to be a positive result. It's going to keep the sign. And then 3 minus 2, that would be a positive result as well. So it's a product of 3 positive numbers here. So it turns out that this thing is going to be concave up, and then concave down, and then concave up. And so that means that I've got a point of inflection that occurs right there at 0 because of the fact that I have a change in concavity. Go from concave up to concave down. And the same thing happens at 2. I have a point of inflection right there. Oops, POI. All right, so there's our second derivative number line graph. All right. One last concept that we need to talk about here is the second derivative test. I guess I'll go ahead and show you the whole second derivative test here. The second derivative test actually shows you how you can use both first and second derivative to tell you whether you have a maximum or a minimum. So the second derivative test says this: if f prime of c is equal to 0 and f double prime is less than 0, then the point c, f of c, is a local maximum. On the other hand, if f prime of c is equal to 0 and f double prime is greater than 0, then the point c, f of c, is a local minimum. So basically what that's saying is if you have a slope of 0 and your function was concave down in the first case, then you must have had a maximum. All right, because your graph must have looked like this, and you hit a slope of 0 right here. In the second case, it says that if you hit a slope of 0 and your function is concave up, second derivative is positive, we are concave up, and we hit a slope of 0 right here, that means we must have a local minimum. All right, on the other hand, if the last bullet there, if both first derivative and second derivative are 0, then it could be a local max, a local min, or a plateau. You got a little bit more work to do, in other words, in order to figure out what that one is. All right. Let's take one last example here. Example 4, we'll add on part D. It says, use the second derivative test to determine if the critical points of function f are a local min or a local max. So if you recall, we already found the critical points of function f. They were at -1 and 0. Let's just go ahead and write down what f of x was equal to again. It was x to the 4/3 plus 4 times x to the 1/3. And so we already know that f prime is equal to 0 at x equals -1. And actually, it's only equal to 0 at -1, right? It was undefined at 0. And so I could determine whether this is a local min or a local max just using the second derivative test, and that is to take the second derivative, which our second derivative was equal to, it was 4/9 x to the -1 or -2/3. And then it was minus 8/9 x to the -5/3. Just make sure you got the right second derivative there. So what we want to calculate is what f prime at -1 is equal to. And if that turns out to be positive, it tells us one thing. If it's negative, it tells us something else. So let's find out what we get. We'll punch that into our calculator. And I'll just punch this into y1. So we have 4 divided by 9 times x to the -2/3 minus 8/9 times x raised to the -5/3. Now I want to evaluate that at -1. And we get a positive 1.3 repeating. That'd be a positive 4/3 is what we end up with. So what our second derivative test tells us, since the first derivative was equal to 0 at x equals -1, I guess I should have written it that way, f prime of -1 is equal to 0. And the second derivative was positive there. That means my function was concave up, and it had a slope of 0 at that point, so this must be a local min. That's what the second derivative test tells us. All right, that's as far as we are going for this second part.